at YouTube's 11 characters. We are at 73 quintillion, 786 quadrillion, 976 trillion, 294 billion, 838 million, 206,464 videos. That is enough.
I love Tom Scott, but recently I found out that this number is not quite accurate. Each YouTube video has an 11-character ID, and each of the character, according to Tom, can have 64 possibilities. For example, this is the ID of my previous upload. I noticed something strange about the last character. If you are watching this video in a browser, please click a random video and open it in a new tab. What is the last character of that video's ID? It seems that we don't have 64 choices, only 16. All characters in the ID are created free, but some are freer than others. The 64 characters are the symbols used in the base 64 counting system. YouTube's version has a slight variation because the standard base 64 counting system has plus and forward slash, and both symbols have special meanings in the URL. But this difference is irrelevant to our discussion, so let's pick the standard one. If we rearrange the characters in a grid of 16 by 4, it is very clear that the last character has to be a multiple of 4. But why? The answer lies in the binary representation of the characters. 64 is 2 to the power of 6, so we need 6 bits to represent a base 64 character. If a character is a multiple of 4, then the last 2 bits must be 0. It means that if we write the 11-character ID in its binary format, only the first 64 bits are free. This explains the limited freedom of our last character. And the total number of combination is 2 to the power of 64. Some of you are having a aha moment, but for others, let me show you a real footage.
How many videos can our platforms put again?
How about a billion? That's a big number.
Only 1 billion videos. Can we have more?
Well, AWS is not a thing until 2 years later, and the maximum number of rows in a single MySQL table is 2 to the power of 64. That is even billions times more than what you want.
2 to the power of 64? That's a huge number. How many videos is that?
That is 18 quintillion, 446 quadrillion, 744 trillion, 73 billion, 709 million, 551,616 videos.
Great. I think people one day will upload their reaction videos to reaction videos to reaction videos, so we are prepared.
After picking a 64-bit ID, the next issue is to reduce the length of the URL. This URL is just too long. We need 2 more characters for the base 64 encoding. Let's just add 2 zeros. If this video represents the case video in the database, then this is a k+1's video. However, plaintext incremental ID in the URL has a big security risk, because people can just enumerate the IDs and get all the videos, including those unlisted, which means people don't want other folks to see. While looking for the encryption method of the IDs, I found this post on Hacker News that confirmed the theory I presented so far. Triple DES, Triple Data Encryption Standard, was the most popular and successful encryption algorithm back in 2004. For simplicity, we can think of Triple DES as 3 layers of DES. In the DES algorithm, we have an encryption key that we can turn a 64-bit plaintext to a 64-bit ciphertext. After the 0 padding, we have the encrypted URL. The DES algorithm is symmetric, which means that we can use the same key for decryption. But the bigger problem is that the key is only 56-bit long, and the total number of combinations 2 to the power of 56 is just too small in front of modern computing power. Some history: the DES algorithm was developed by IBM in the 1970s. There are rumors that the NSA planted a backdoor in the algorithm, but that's beyond the scope of this video. Anyway, what happened in 1998 is that Electronic Frontier Foundation, a non-profit digital rights group, created a machine called DeepCrack. And this machine cracked the DES algorithm in about 56 hours, and that's what we call a reasonable time. As a consequence, the DES algorithm was retired in 2005. The triple DES is much more secure with a longer key length, but due to various reasons, it was still disallowed after the end of 2023. Here is a thought experiment. What will happen if the triple DES algorithm is cracked? The first video on YouTube is me at the zoo, and we have its published date. And we also has the ID's ciphertext, the video ID. Suppose this video is a case video in the production database. We can make a safe assumption that the earlier the video is, the smaller the K is. About 25 minutes later, a second video is on YouTube. And this video is likely having a primary key of K+1. Imagine we can find a sequence of consecutive videos, likely in the early days of YouTube. We can ask the question, is K 1, 2, 3, or 4? If you find one matched pair, then you'll find a lot. But this idea is actually stupidly naive. The assumption that the triple DES can be cracked in a reasonable time is likely to be false in the next few decades. YouTube, of course, knows the related security risk, and the incremental ID was already abandoned many years ago. As for the early day videos, it's actually very hard to find the order. The YouTube Data API only gives you the published date, and if you ever upload a video to YouTube, you know that the ID is generated the moment you started uploading. There's no way to collect the upload timestamp data. For now, let's forget about this imaginary security risk. If the IDs are high-quality random numbers, when will there be a collision? To find the number, we go back to the good old birthday paradox. The counterintuitive birthday paradox says it only requires 23 randomly selected people to have a 50% chance that two of them share the same birthday. For n people, let's calculate the opposite of what we want, the probability that none of the n people share the same birthday. This calculation looks trivial, but surprisingly it only requires 23 terms for this product to be less than 1/2. The same formula can be used to calculate our YouTube question. But this time we have to make some approximations as the number is just too large. When x is very small, 1 minus x is roughly e to the power of negative x. Small n is also very large, so n squared minus n is just n squared. Suppose we are looking for a 50% probability, then small n is approximately 5.1 billion. It means that when the size of YouTube reaches 5.1 billion, there's already a 50% chance that there is at least one ID collision. The question now is, how do we know the actual size of YouTube? There's no official data, and numbers like this one doesn't help much. However, because of the ID's randomness, we can approximate this ratio by generating a bunch of IDs and see how many of them actually hate a video. I do not recommend you to write a script to do it. It's not about being banned by YouTube, it's just not mathematically efficient. Even assuming that there are 18 billion videos on YouTube, the chance that a random ID hits a video is still 1 in a billion. The probability is so small that one can comfortably challenge the whole internet that changing one character in the ID does not result in another ID. The chance is low, but not zero. Two researchers, Professor Zuckerman and Dr. McGrady, took this challenge. They took a sample of almost 26,000 random YouTube videos, and they found some amazing statistics. And the discussion on the statistics will be for our next time.